Okay, let's get started. So, um, right. So at this point, you've now been introduced to derivatives, and perhaps you also went ahead and watched some of the videos where you actually go through the derivative rules. Um, the first two problems here involve calculating the derivative without the derivative rules, just using the limit definition. And then afterwards, I think everything else we just, well, no, there's a few more, there's at least one more problem where you use the limit definition. But at some point, we start to just use the rules of derivatives, the product rule, the quotient rule. And um, yeah, it's a good idea to familiarize yourself with these rules as quick as possible. You kind of have to memorize them. Um, but I'll introduce them as we encounter them in this problem set. So let's go ahead and start with number one. We have limit definition of derivative of, in order to calculate the derivative of x to the negative first power, or 1 over x. So I think before this, let's first let me introduce the rule in general. So this is called the x power. It's not power. Well, I get, yeah, it's power rule. Power rule. All right. So if you have x to some power n, where n is just a number, it can be an integer, it can be a rational, meaning a fraction, it can be a real number. It's just n times x to the n minus 1. You have to remember you drop the n down as a coefficient, and you have to subtract by 1 in the new x. Okay. Where did the ribbon go? Yeah, maybe I'll do that. Okay. So right now, limit definition. So how do I want to say this? Well, we've been sort of extracting f as a function of, or yeah, writing it as a function of x and then saying it's limit, or f prime of x is equal to limit as h goes to 0, f of x plus h minus f of x all over h, right? The only difference between this and what you encountered in the previous homework set is that in the previous one, you had numbers here. You had a, where a is some number. But here we're treating the derivative as a function instead of just a number. Because the idea is, in that process, in the previous section, you could have created that tangent line anywhere along the function. And so the resulting number actually has a dependency based on where you centered your tangent line, which basically says that it's a function of wherever you're placing it. It's a function of x. Okay, right. So now we've got this definition. It's not too different, right? And so we just go ahead and we crank through this definition. So just like before, we need to substitute into f these x plus h and this x. So we have x to the negative first power. I would definitely want to write this as a fraction. And then, of course, this is all over h. And then just like before, we're going to want to get rid of these denominators. So we'll multiply by x plus h times x. And of course, we have to do the same in the denominator. And so this will simplify. We get x minus x plus h all over h x plus h. And then you can see that things will simplify quite a bit. So this x and this minus x will cancel. And then you can also notice that there's a h in the numerator, which will cancel this h in the denominator. To save time, I'm going to just do this as a second step, but I'll do it in a different color. So notice that the end result you'll have is a negative 1 in the numerator. Okay, so you got negative 1 over x times x plus h. And so you get a negative 1 over x squared when you take the limit. And this checks out because we can use power rule to just verify, like, what would the derivative be if we were to do this using power rule. Let me, introduce my notation for derivative, which is just an arrow with a d on top, or off to the side if I draw the arrow vertically, just a way to shorthand writing derivative. And so power rule would say you bring this -1 down, and you have x, and then you decrease by 1. So you subtract 1, you get x to the -2. And notice that this matches exactly. Okay, so we can be doubly sure of that our calculations are correct. All right. Okay. Next, let's see. We've got this. So I'll do the check later. So again, we want to do the same process. So we extract out what is the function we're trying to take the derivative of. The function is square root of x. And we recall the limit definition of derivative, which says it's limit h goes to 0, f of x plus h minus f of x all over h. And then we go ahead and plug into our definition. So square root of x plus h minus the square root of x all over h. And okay, let me ask you, since I sort of spoiled it the first round, what do I do from here? You can type
conjugate.
it into conjugate. Yep, that's right. So we go ahead and multiply by conjugate. There's something on my screen I don't want on my screen right now. Okay, I'm trying to grab the colors, but I can't see the colors. All right, there we go, finally. Okay, yeah, so multiply by the conjugate, square root of x plus h plus square root of x all over x plus h plus square root of x. And so then the next step we have, the square roots will square away. So the numerator is going to be x plus h minus x. Maybe I'll put colors just because it sort of helps to see like that these are coming from squaring the square roots. And then the middle terms, they cancel each other, right? That's exactly why multiplying by the conjugate is helpful. Okay. Then we've got in the denominator, well, the denominator still looks kind of messy, but when you take the limit, this will simplify. Okay, also then we got some cancellation here, and you have a h on top, h on the bottom, so the h's will cancel. You've got that's going to turn into a 1, and you'll have square root of x plus h plus square root of x. And then taking this limit, you get 2 square root of x. Right. And just to double check this, well, if we want to use power rule, we want x to be raised to some power that is a number, right? So square root of x, I hope you remember, is a 1/2 power. Take the derivative. Well, according to power rule, it's you bring the power down, and then you decrease the power by 1. So you get a -1/2. And these two are the same thing, right? Because you should remember that a negative power is actually just put the thing into the reciprocal or into the denominator or flip it, basically. Yeah, so if it's in the numerator, you bring it to the denominator and vice versa. And so you see that these two are actually equal. Maybe I'll also denote that so we can put a check mark. Okay. Any questions so far?
The h's canceling each other out is how you get that 1 on top, right?
That's right, yeah.
Okay.
So yeah, when you simplify this, you just get an h on top and an h on the bottom, and you can just imagine dividing these h's to cancel them. Yeah. Okay. Right. Number 3, A and B, they are both using power rule. You can sort of see that all of these are x to some power, t to some power. So we're just using power rule here. And the only thing is that we might want to, or really we should, rephrase x in the denominator as being a negative x, just to make it easy for us to like keep track of. So this is actually a 2x to the negative third. And I guess we'll go ahead and say this is minus 6t to the negative 3 halves. Okay, so when we calculate the derivative, we will, maybe I'll just rewrite it here. X to the n is going to turn into nx to the n minus 1, just as a reminder. And so, okay, just to make sure, yeah, what is the derivative of this? The 5x cubed. Someone? Good, yes. So normally though, when you type it, you would say you would use the caret symbol. So it's the shift number 6 is how you would do it. You don't have to say to the power of, but yes, very good. 5x squared. And then this guy, so I guess the thing I was trying to see that you understood how to do is like you multiply the 5 and the 3. So when you bring the coefficient down, it's going to multiply with the other coefficient. So in this case, you got a minus 3 that will multiply with a 2. You got a minus 6x. And then always remember you're subtracting 1, right? So minus 3 subtract 1 gives you minus 4. I've definitely seen people go the other way around. I've definitely seen people mess up subtracting from a fraction. So like if you have 1/3 and you subtract 1, you should get negative 2/3, right? Okay. This last term, maybe it's meant to trick you. Notice that this is just a constant, right? This is just some number. And the derivative of a constant is just going to be 0. So that term disappears when you take the derivative. Okay. So I guess we could box it. I haven't been boxing today. That's fine. All right. Then the next one. So derivative of this, I won't ask you to say just because you can multiply, right? 21 over 2, and then t. And so just to double check, what is the exponent supposed to be?
1/2, right?
Yes, 1/2. Good. You can subtract 1 from a fraction. Very good. Yeah. It's surprising whenever you aren't able to do that. I find that surprising. Okay, so multiplying this, notice that it will reduce, right? So you'll get 18 divided by 2, so 9, and then t, and maybe this is a trick question, but how do you subtract 1 from negative 3 over 2? What do you get? Anybody?
Negative 5 over 2?
Exactly. Very good. Yeah. Okay, great. Maybe it's trickier when the denominator isn't just 2, but it's like 3 or 7 or something. I should make that look more like a 5. All right. Okay, and we can just box that. Great. We're going into, okay, yeah. Throwing a ball. Okay, yeah, so this problem has a lot of parts to it, and the numbers are actually not very great. You'll see that when we get to part B, but part A is straightforward. It's just limit definition of derivative. We're given y, well, we're given y, we want to find y prime. Actually, all of the first 2 lines are just some flavor text. You don't really need that, I think, except to note that it's feet per second. So, okay, limit definition. Well, we've been using f prime, but this time, since the problem is in terms of y and y prime, I'm going to use that. Limit as h goes to 0 still. And then it's going to be y of, in this case, it's t plus h minus y of t all over h, right? I'm using the same variables that the problem is posed in. That hopefully isn't too tricky. And well, now we have to plug into this thing. Minus 16t plus h quantity squared plus 50t plus h plus 5. And that's just the first evaluation. Now I need to subtract off the second evaluation. But thankfully, it's just y of t, so I just can copy it directly. T squared plus 50, t plus 5. And well, oh, I forgot limit here. H goes to 0 over H. Okay, so it looks like I'm gonna need a little bit more space. Limit as H goes to 0. We can expand that out, minus 16 t squared plus 2th plus h squared plus 50t plus 50h. I didn't really need to expand that. Plus, well, actually, let's just cancel those. I could have also canceled the 50th, in fact. Whatever. Plus 16t squared minus 50t. Okay. This plus 16, this minus 16t squared, and then this minus 50t and this plus 50t will cancel. And let's just double check. So the resulting terms all have h, which will cancel with this h. That looks good so far. Okay, I'm gonna drift downwards here. So let me do the cancellation mentally also just to save space. So we're going to distribute the 16 and then we're going to divide. So we get minus 32 t minus 16h plus 50. Okay, so I sorted the two steps in one there. Actually, there's supposed to be an h somewhere. Yeah, no, this is not a t, this is an h. I think I said h, but I wrote t. Yeah, that's right. Okay, and now we take the limit, this term disappears, and we're left with negative 32t plus 50. This is the derivative that we're expecting. You can also just use the power rule on this function, and you get 50 for this term, you get minus 32t for that term. So very easy check that this is the right derivative. Okay, does this make sense so far? No questions? Okay, so now we start to get to the mess of this problem. So when is the derivative greater than 0? When is the derivative less than 0? So the technique that I want to show you first is it's a technique that relates to what you'll be using later on with like curve sketching, which is to use a number line and to basically, well, first you start by solving y prime of t equals 0. And then this gives you place marks that you put on your number line that you then you divide your number line into intervals, and then you can test those intervals to determine when is it greater than and when is less than. Because y prime equaling 0 is going to serve as the places where it transitions from being greater than to being less than. Okay, so we're going to just quickly do this. Shouldn't be too hard. Equals 0. We then solve, so then we get t is equal to 50 over 32. Right, I just move the minus 32 to the other side by adding by 32, and then I just divide by 32. And simplifying, we get 25 over 16. And you could write seconds after this because there are units. So this is already not a very nice looking number. Then you draw your number line. This is a number line in terms of t, or should I, well, actually the number line, the way I normally write it is I write what I'm going to evaluate on this number line. So that's not what I want to do. This is 25 over 16, and y prime, what will it be on this interval? Well, notice that we're looking at this function. Okay, so if we plug in 25 over 16, we'll get 0. What happens if I plug in something greater than? Well, the negative is going to dominate, and so we expect a negative value. If we plug in something less, you can, well, for less, you can easily just say choose 0, and then you get 50, so you get positive, right? So you can kind of answer this, and you'd kind of be technically wrong because this is a real world problem. And if you actually then read the details of this, well, it's a softball that's being thrown, and then there's a bit of a clue that at some point it hits the ground. Okay. Well, this complicates matters because then we have to think, okay, when does y equal 0? When does this function y of t equal 0? Because obviously at some point it's going to hit, at some point it will hit the ground, and then afterwards it'll be traveling through the ground, which is not allowed, right? So we kind of need this endpoint, and then that makes us also think, oh, well, the obvious starting point is t equals 0 because we're not measuring anything before launching the ball, right? So things get a bit more complicated here. Just to make sure, so I'll write, like, we kind of need to solve for y of t equals 0. So solve this. So who can tell me how we would solve this, right? This is just some quadratic. So how do we solve a quadratic? How do we find the roots of a quadratic? Do you plug 0 in for t? That will not work. That'll give you the initial height in this case. So maybe just to make sure this is clear. So we have some kind of a quadratic like this. Plugging in 0 is going to give you this, but we're not interested in this. We're interested in these two guys. Set the, yes, I did that. I'm asking you how do you solve this algebraically? So, okay, you shouldn't pause quite so much for this. So you definitely know this word. Quadratic formula. Okay. So you should at least remember there's something called the quadratic formula that for a general quadratic, which this is, right? So I'm gonna need some margin space. I guess I'll go to the other side. Right. So for any quadratic, RATIC, y equals ax squared plus bx plus c. The roots, which is like what values of x make it equal 0. They are given by the formula x equals, and then, hopefully you can just recite this, minus b plus or minus the square root of b squared minus 4ac all over 2a. Right, this is a, I don't know, if I put a box, is it gonna actually put a box? That's my question. Oh, it does. How nice. Right, this is the kind of thing that I think you have it drilled into. Or you can, probably just let a calculator do that. But assuming that you don't have a calculator, this is what you would use in general, right? There are situations where it's much nicer, where your quadratic actually factors, and then you can just read off the roots from the factorization. That's sort of a special technique that only works if the quadratic is factorable, but this guy is not factorable. It's kind of nasty what you get. So I'm going to write what you actually get. Yeah, okay, so this root, right? I think it also, you don't get 0 in this case. I think it does actually line up like this. I don't remember plugging in. No, you definitely don't get 0 because if I plug 0 in, I get 5 according to this formula. So yeah, there's another root when time is less than 0, but we ignore that. For the other root, we get 25 plus the square root of 705 all over 16. You can double check that. It's just a calculation, really. Well, maybe it's a little bit more complicated because like you normally in the denominator you get 2 times 16, but then there's some reduction that happens. Yeah, but so I'm going to use the approximation for this. This is approximately 3.22199. And I'm going to be using that. So now that we've gotten all the details for the number line, we can actually answer this problem accurately, right? Otherwise, like normally you would say, oh, it's minus infinity to 25 over 16 for one of them, and it's 25 over 16 to plus infinity for the other. But because of this being like a real world problem, I guess I'll use a different color just so that, because it's a little bit crowded. So y prime is greater than 0 for the interval 25 over 16 to 3. It should be an open, shouldn't it? Because it's equal to. I'll make it open. 3.22199. And then this is y prime less than 0 on the interval from 0 to 25 over 16. So this is the answer for the problem if you're trying to be really technical, right? If you assume that the ball doesn't travel through the earth, which it shouldn't. Okay. So questions on this? Just want to make sure that I haven't lost anybody on the algebra. Do you remember quadratic formula now? Hopefully it's giving you some flashbacks of some sort. Hopefully not so bad ones. Yeah, okay, I'm not hearing anything, so I guess I'll keep going. So part C is asking for when is it going upward and when is it going downward. That's basically just reinterpreting B, because this derivative is a change in height, right? So if the change in height is positive, that means it's going upwards. Height is increasing. So we basically copy down the same exact thing, except we're just sort of relabeling. So upward is derivative is positive, so it's going to be the 25 over 16 to 3.22199 seconds. You could say seconds somewhere, maybe. And downward is, wait, no, I think I labeled it wrong, didn't I? Yeah, okay, I labeled it wrong, sorry. I need to flip these. Someone should have caught me on that. This one, less than 0, right? Negative means less than 0. And so, yeah, and this one is greater than 0. So it's, I guess I'll erase this. Downward and upward. So from 0 to 25 over 16. Okay. Next, what time does the ball reach its maximum height? So, well, when you think about maximum height, you think about a ball, like you're thinking about the vertex of the parabola, the very top, like pictorially, it's this point right there. In terms of calculus, what you can do is you can think of it as being, when does the derivative equal 0? So because over here in this region, the height is still increasing. Then it levels off. Then the height stops changing for an instantaneous, like just for a single moment in time. And then it starts to decrease, which means that the ball starts to fall. So really the maximum height occurs when y prime is equal to 0. And so we can answer this as being, I'll just keep using blue, that's fine. T is equal to 25 over 16 seconds. Right, that time is precisely when the ball is at the vertex of the parabola. All right, and then maximum, what is the height? What is the actual height? So how do we do this? Well, you should think, you take that time that you know it's at, you've got this function, you plug in, right? That's all you need to do. So you take y and you plug in 25 over 16. And I'll say I definitely use the calculator for that because I don't really want to deal with all that calculation work. But you could do it by hand if you really wanted to. 1955 over 16 feet, which as a decimal approximation, you would get 122.1875 feet. So actually, this isn't approximately, this is exactly equal. Dividing by 16 will give you a precise decimal. So you could use either of these answers. Okay. Any questions on this whole problem? We might be able to get a few more problems in. No questions. Okay. Okay, so 5A. Well, when you read this problem, maybe I'll read it to you. Blah, blah, blah. You price your download at C cents, and if you price it at C cents, your song will be purchased this many times. And you want to create a formula for the revenue. Okay, so revenue, hopefully you know it's just a real world concept, is price times quantity, right? That's going to be how much you actually generate, how much money you actually generate. So R of C, R is a function of C because we actually have like the number of times purchased as a function of this C. And so all you need to do is multiply the two things together like that. But then for our derivative, we may as well distribute this over. So we get 5,000 C minus 100 C squared. Okay. Now the derivative, well, it doesn't ask for limit definition. That's good. We can just take the derivative using the power rule. So this first term becomes 5,000. And then this term becomes minus 200C. So hopefully you could do it. Maybe you take twice as long to do that calculation, but it's that fast, right? So, okay. Now we need to also determine when is this function positive, when is this function negative. So we do this number line test. We'll set it equal to 0. 5,000 minus 200 C, set it equal to 0. What is that going to give me? I'm going to put an implies arrow here. We would move this 200C to the other side, divide, so we get C is equal to 5,000 divided by 200. And you can cancel off the zeros. You would get 50 over 2, which is just 25. Let's put units down. So this is measured in cents, 25 cents. Okay. And so now we can mark a number line. Maybe I'll give myself a little bit more space for the number line. R prime at 25 cents. So I'm thinking about this function and noticing this is negative. So if I put something that is greater than 25 cents, it's going to be even more negative. So we get negative here, we would get positive on this side. So R prime of C is greater than 0 for, and also now notice we've got this. So this actually tells us what C is bounded between. So it's between 0 and 50. We don't really expect to plug anything outside of these limits. And so, okay, that will give me 0 here and 25 here. And then R prime less than 0 is going to be from 25 to 50. Notice that I'm using I'm using a closed paren and an open paren, and that's because we are actually able to plug 0 in and get a value that makes sense. Like we plug 0 in, we'll get 5,000 for R prime. That is going to be positive. So we do include 0 for this interval. And for this interval, we can plug in 50 and we'll get something that's quite negative. And so we do include 50 in this interval, but we're not including 25, at least I'm not, because at 25, R prime is equal to 0, whereas these are strict inequalities. So I'm writing it like this just to be precise. Okay. Now for part D, interpret the meaning. What should you charge? If you want to maximize your total revenue. I think interpreting is just basically what the question is asking afterwards. So hopefully what you can see from this is, yeah, up to a certain point, the change in revenue is increasing, and then at 25, it levels off. And then if you start charging more than 25 cents, your revenue is expected to decrease. That's what this is saying, right? So you should charge, so I'll write down, should charge 25 cents to maximize revenue. That's what you can conclude from this analysis. And then how much total revenue you generate, total revenue, well, how would you calculate that? If you are going to use 25 cents, then you plug that into the function for revenue. Oops. You plug it into the function for revenue. And that formula is right here. So I'll just write it down. 25 times 5,000 minus, I think I can calculate this mentally. Yeah. So 25 times 25,000 or 100, yeah. 62500, I think. Yeah, that's what I got before. 6500. And important to note is what are the units here, right? So this is still in cents, okay? So then it makes a lot of sense to convert that over to dollars, right? So this is actually $625. And I would box this guy. Okay. So any questions on that? Um, 1, 2 pages. We did almost 3 pages. I think we should be able to finish the last, this number 6. There's 3 parts to it. We should be able to finish that before when we end. Okay, so yeah, at the very least, I'm going to introduce to you product rule and quotient rule. So these are 2 rules that we need in order to tackle this set of problems, and actually, I think all the problems afterwards. Yeah, so here are some new derivative rules. So product rule. So the idea is you have a product of 2 functions, and you want to take the derivative of this. So if you write it out in full, what you're saying is you want to take the derivative of a function f times a function g. You're trying to do that. And fully expressed, this is what the rule says. F prime times g plus f times g prime. Okay, so it's not as nice as what you would hope it to be. You would kind of hope it's f prime times g prime. That is not true. This is true. But as a shorthand, I will show. I'll write down what I normally would for memorizing, which is just this. Recall that the prime means derivative is another notation for derivative. So I'm just suppressing the fact that these are very with respect to x. And so then f prime g plus f g prime. Right? This is a much shorter way of writing the above statement, so long as you know that the second means the first if you expand everything out. So this is product rule. The other thing you need to know is how do you take the derivative of a quotient of 2 functions. So we got a quotient rule for that. And you know, if you went through the lecture videos, you'll seen this. If you went through the slides, you'll have seen this. I'm just saying all this in case you haven't done so already. So, yeah, I'll write it out in full. Right. So derivative of this quotient is f prime g minus f g prime over g squared. So there are a few important things to note about this one. So quotient rule is the harder formula to remember because you have to get this order correct. You have to, if you swap those two around, you'll get the negative of the correct answer, which most of the time is going to be wrong. Also, you have to remember this squared in the bottom. That's not so hard to remember, but this ordering is important. There, I would say try to come up with a mnemonic that you can use, that you can remember. For me, maybe I'll show my mnemonic. So it's a stupid thing. So I kind of remember it like that. And one thing that I do here is I actually swap the u and the d. I swap the two things that are being multiplied in the first term because usually you want taking the derivative to be the last thing that you do because of one thing that you'll learn about soon, which is the chain rule. So the derivative may expand out into taking a couple of derivatives because of chain rule. And so it's always nice to have the derivative thing happen last. And so I do that, and you can see that this spells dude in a really stupid way. So that's my weird mnemonic. But however you want to memorize it, another thing you can see is that, for example, if you write it in this way, this matches up with product rule precisely. You just have to remember where the primes go and always write it in this order. And then going from product to quotient is simply just turning that plus into a minus and remembering that you have denominator. Right. Take your pick on how you want to memorize these, but you kind of need to know them. Okay. We have 5 minutes. Maybe I'll be able to get through one of them, and then we'll continue. All right. So doing these, the first two are at least a direct application of these. C, I can expand on a little bit more. It just uses a generalized product rule, or it uses product rule twice. I'd probably just show you the generalized version. Okay, but let's go ahead and try to compute this using this product rule here. So maybe I'll say this first function, this first guy, this is f, and this second guy is your g, right? So you remember f prime times g plus f times g prime, if you're getting used to it. So f prime is going to be 2t plus 1 times, and then g, you just copy it down explicitly or directly. And then remember plus, and then f times g prime. F we just copy down t squared plus t plus 1 times, and then g prime. So 12t squared plus 1. I guess just to be helpful, I will also label these so that you can see like this is what I'm doing. So you can see that this is the product rule taking place. But that's like, you should, with enough practice, you get to a point where you don't need those kinds of labelings, and you can just sort of execute the product rule more or less without thinking so much. Actually, we have enough time to do quotient rule, so let's go ahead and do that. So this guy on top is my f, this guy on the bottom is my g, and we're going to recall what the quotient rule says. So I'll try to do it in the standard order. So f prime g. Yeah, see, I really don't like that order. I'm going to do it in my order. Forget that. Okay, I'm doing it in my order. So x to the 4 plus 7x squared plus 3 times, and then f prime. So it's going to be 6x plus 2 minus, and then f times g prime. So it's going to be 3x squared plus 2x times, and g prime is the 4x cubed plus 14x. And this is all over g squared. So I have to square that polynomial. Okay, so I take this guy, I square it. Okay, and so compare that with the formula. The formula says, well, what I did here was I need a bit more space. Let me lasso this. That should be enough space. Yeah, so what I did was g times f prime minus f times g prime over g squared, which matches with this guy, except I just swap the f and or f prime and the g. Okay. Well, we're 1 minute away from the end. So are there any last questions? If not, we'll stop here. Okay, I'm gonna stop the recording.